This video is part of the Membrane Versus series, and this one looks at membrane technology as a disinfection process, comparing it with chemical disinfection and UV irradiation. Disinfection is the significant reduction of disease-forming microorganisms or pathogens, normally by several orders of magnitude. This is to be distinguished from sterilisation, which is the elimination of all microorganisms. The extent of disinfection is often expressed as the log removal value, or LRV, the log of the ratio of the feed to treated water concentration. So, for example, if there are between 10,000 and 100 million more pathogens in the feed water than in the treated water, as is often the case, then the LRV would be between 4 and 8. There are three recognized ways of achieving disinfection or removal of pathogenic microorganisms or pathogens: attacking the cell wall with chemical oxidants, stopping the pathogen from reproducing by attacking the DNA, or just sieving them out. The first of these is most widely achieved using chlorine, with ozone and chloramines also used and which act similarly. UV irradiation acts by penetrating the cell wall and breaking the bonds of the organic bases in the cell's DNA. Membranes simply physically remove the microorganisms, along with anything else larger than the membrane pores. The effectiveness of all of these methods is impaired to some extent by other water constituents. Oxidizing chemicals like chlorine react with oxidizable species in the water, specifically organic matter, which exerts an additional disinfectant demand, i.e. requires a higher dose of chemical than that needed for disinfection alone. This not only increases the disinfectant dose required, it also increases the tendency to form undesirable disinfection byproducts, or DBPs. Some of the DBPs formed from chlorination, notably trihalomethanes and trihaloacetic acids, are genotoxic. They can cause cancer at high concentrations and or long exposures. In the case of UV disinfection, materials in the water which absorb UV light impair light transmittance and so reduce the UV dose. Also, minerals like ferric oxide and other compounds can build up on the surface of the UV lamp over the course of time, and this fouling layer also reduces transmittance. Most UV systems have a mechanism for periodically wiping the UV lamp clean. For membranes, there's no similar reduction of disinfection effectiveness by other components in the water, provided they don't actually damage the membrane or module. However, fouling of the membrane surface, or else plugging of its pores, by particulate and colloidal matter reduces the membrane permeability. This increases the membrane cleaning frequency and lowers the net flux, which has cost implications. To sum up, all disinfection processes are subject to constraints on their effectiveness and or economic viability imposed by other contaminants in the water. For oxidative chemical disinfectants, and chlorine in particular, organic matter in the water generates undesirable halogenated DBPs. Suspended materials, as well as sparingly soluble minerals, reduce the effectiveness or productivity of UV irradiation and membrane filtration through fouling. Of the processes considered, only chlorination and chloramination provide a residual disinfection, remaining in the water for several hours after dosing. Chloramine, formed from the combination of chlorine with ammonia, has a lower DBP formation tendency than chlorine, but is generally a less powerful disinfectant. Lastly, there are question marks over the determination of LRV when the pathogen is undetectable in the effluent. But that's another story.